The core is reversing. The quantum sensor countdown has begun. The alert came from a lab most people in physics hadn't heard of. A ring of quantum sensors whispering that Earth's magnetic heartbeat had slipped off tempo. Not a storm, not space weather, something deeper. If they're right, quantum devices might spot the next big magnetic shift before geology writes it in stone. That matters because the field is our radiation shield. If it falters, satellites glitch, power grids strain, navigation drifts, and biology feels it. We'll chase those faint signals down to the core, through covert sensor networks, stubborn anomalies, messy simulations, and real stakes. To understand why, we have to go deep. Roadmap and commitment, escalating revelations. First, the engine. Earth's magnetic field isn't a static shell. It's forged by a liquid metal ocean 2,000 miles down. Convection, rotation, and electric currents combine into a self-sustaining dynamo. Over the last 180 years, the dipole's strength has declined on average by about 16 nanotesla per year. That weakening is uneven, and the geometry has been shifting faster than expected. Second, the cracks in the dashboard. The South Atlantic Anomaly, a weak patch over Brazil and the South Atlantic, keeps evolving. It has split into western and eastern minima, with the western lobe drifting roughly 3 degrees per year. Meanwhile, the North Magnetic Pole sped up, sprinting from Canada towards Siberia fast enough to force an early world magnetic model update before the 202's window closed. Third, the ears for whispers. Quantum magnetometers, atomic vapor cells, diamond NV centers, and cryogenic squids read magnetic fields down to femtosla. Networked as gradiometers, they strip away local clutter and leave slow, deep signals. Fourth, the oddities. When these meshes went live, they detected ultra-low frequency drifts and phase quirks that didn't match ionospheric patterns, daily cycles, or crustal induction. Fifth, the referees. Satellites like Swarm, plus calibrated platform magnetometers from missions such as Cryosat-2, cross-checked the shapes. Paleomagnetic records added long memory. Some fingerprints match the core's secular variation rather than the sky. Sixth, the futures. Simulations, anchored by data assimilation, show several paths: a full reversal across thousands of years, a shorter excursion, or a wobbly stabilization. The difference shows up in how flux patches and deep waves couple. Seventh, the stakes. Weak field zones raise satellite radiation hits. Grids face storm-driven currents, aviation reroutes, navigation models age faster, and magnetosensitive animals adapt. We will separate hype from signal, name uncertainties, and track what's changing now. First, the engine. The core dynamo, how the shield is forged. To understand the field, think of an iron-rich ocean at outer core depth, hotter than lava, but squeezed by pressure so intense it never boils. Heat leaks upward from the deep earth, and the inner core slowly freezes at the center. That freezing releases latent heat and light elements, which make the surrounding fluid buoyant. Buoyant fluid rises, cooler fluid sinks, and massive loops of liquid metal overturn. Because the metal conducts, motion through any magnetic field generates electrical currents, and those currents reinforce the field. That feedback loop is the geodynamo. Earth's rotation shapes that motion. The Coriolis force organizes flow into helical columns, Taylor columns, aligned roughly with the spin axis. Seed fields, however small, get wound and stretched by twisting currents. The growing inner core helps by providing steady buoyancy and heat. The system is messy and turbulent, but it sustains itself. Reversals aren't malfunctions, they're part of the engine's long story. Lavas and sediments show many flips, irregular in timing. Sometimes the field only staggers, an excursion, before recovering. The mechanism isn't clockwork. Small changes in flow can push the system across thresholds where the large-scale dipole weakens, fragments, and reassembles with opposite polarity. Right now, the surface pulse is changing. Since the 19th century, the dipole has weakened on average by roughly 16 nanotesla per year, but not evenly across the globe. The North Magnetic Pole accelerated from the Canadian Arctic towards Siberia. Meanwhile, the South Atlantic sector developed the weakest field at satellite altitude, with a split into western and eastern minima over the last decade. Operators know this because their satellites feel it. Why do tiny flow changes matter? The dynamo's feedback is nonlinear. Look at flux patches, regions where field lines concentrate near the core mantle boundary. As the outer core's flow shears and advex these patches, they drift, merge, or split.
If reverse polarity flux grows beneath southern Africa, the surface above weakens. Those patches interact like weather systems, except the air is molten metal and the timescale
is years to centuries. Waves ripple through this metallic ocean. Torsional Alfvén waves, cylindrical axisymmetric pulses, carry angular momentum along columns. Satellite and observatory records point to subdecadal periods. Think roughly 6 years for notable trains. These waves modulate rotation and subtly modulate the magnetic field. Other magnetocoriolis modes tilt and wobble, adding interannual wiggles. We've resolved some of these signals in satellite secular acceleration maps, a sign that the interior can shift gears faster than old textbooks suggested. The mantle's influence matters. The core mantle boundary doesn't leak heat evenly. Above, subducted slabs cool some patches. Hot plumes warm others. That patchiness corrals convection into preferred lanes. It's like a textured ceiling guiding the flow below. The result is preferred corridors for flux patches and a tendency for features to drift west in certain belts. Can we predict a flip? Not on a schedule. The system is chaotic. Data assimilative models ingest observatory and satellite data, reconstruct core flow, and project a few years ahead. Those short forecasts map how flux patches drift and where waves might phase next. Beyond that, uncertainty explodes. But short horizons still matter when you're managing satellites, grids, and routes. There are telltales. If reverse polarity flux near southern Africa expands and links westward, the global dipole weakens more broadly, and the surface shows a widening weak field belt, not just a deeper pit. If torsional waves arrive in phase with patch encounters, we should see small, patterned accelerations in specific regions before bigger geometry changes. If the South Atlantic's double minimum grows and spreads, satellites will log more radiation hits, and ground stations will see unusual secular variation phases relative to ionospheric drivers. This is where quantum sensors earn their keep. The surface field is a sum of sky, crust, and core. Strip off the sky with models and indices, suppress local clutter with gradients, and what remains femtosla to nanotesla shifts over months to years, carries the interior's signature. Atomic spins, diamond defects, and superconducting loops hold stable references that let us average for a long time without drifting. If the engine is messy, the dashboard is stranger. And the next chapter is written in anomalies. The anomalies, the South Atlantic Anomaly, and fast pole drift. Before dawn over the South Atlantic, satellites cross a patch every operator knows by heart. Instruments down mode, memories scrub, error counters tick a little faster. That footprint, stretching from southern Brazil across the Atlantic toward Namibia, is the South Atlantic Anomaly, the field's softest spot at satellite altitude. It isn't a tidy circle. Over the last decade, it's split into two minima. A western lobe sliding west at roughly 0.2 to 0.3 degrees per year, and an eastern lobe near southern Africa that deepened faster. Mission planners draw red zones on orbital maps and route sensitive operations around them. Here's the human side. Hubble schedules downtime through SAA passes. Earth observation constellations expect data dropouts and budget for extra downlink attempts. Star trackers slip more often. Detectors saturate. Single event upsets and bit flips cluster by longitude, not by day of the week. Operators already use solar forecasts, but the SAA's baseline weakness doesn't follow the sun's calendar. It follows geography. Over years, a few % less shielding adds up to shorter mission life and tighter margins. Underneath, the physics points down, not up. At the core mantle boundary beneath southern Africa and the South Atlantic, reverse polarity flux patches persist and drift west. As they slide, the surface field above them weakens. In recent satellite field models, that weakening organized into the current double minimum, western and eastern pits that don't move in lockstep. The western minimum has crept westward. The eastern one deepened with little east-west motion. That asymmetry fits simulations where reversed flux threads different corridors guided by patchy heat flow at the boundary. Meanwhile, far to the north, the pole broke its slow habit. For most of the 20th century, the North Magnetic Pole wandered through the Canadian Arctic. Then it accelerated, arcing toward Siberia. That sprint forced an early world magnetic model update before the regular 5-year cycle ended. Surveyors, drillers, and pilots felt it as a creeping heading error that outpaced paperwork. The pole's path reflects a tug of war between high-latitude flux lobes beneath Canada and Siberia. When the Siberian lobe strengthens, the pole races that way. When the Canadian side recovers, the sprint kinks or pauses.
Traditional models explain parts of this, but not the choreography. They capture westward drift and the link between reverse flux under southern Africa and South Atlantic weakness. They tie pole motion too,
changing high latitude lobes. What they struggle with is timing. Why the SAA split when it did, why one lobe deepened faster, why the pole's speed jumped, and why brief stalls appeared. That's where deep waves matter. Torsional Alfvén waves and other magneto-Coriolis modes modulate flow. When a wave arrives in phase with a pending patch encounter, surface secular acceleration spikes locally. When it misses, things quiet down. The result is a pattern of interannual wiggles layered on slow drift. Space weather complicates the read but doesn't write the script. Storms swell the belts and make the SAA nastier for a day or two, then pass. The anomaly's core footprint stays anchored to the same longitudes. Operators see it in logs. Storm spikes come and go. The baseline risk follows where you are. That's why they pair solar alerts with geographic risk maps, and why any hint of westward expansion matters for scheduling. The ground view joins in. Mid-latitude observatories around the Atlantic log small, phase-coherent accelerations. Sub-nanotula, but stubborn, leading periods when satellite maps later showed the SAA's shape reshuffling. Those drifts thickened before the eastern minimum deepened, then relaxed after. Up north, stations along the pole's path reported shifts consistent with swings in influence between Canadian and Siberian lobes. The timing wasn't perfect, but the rhyme was hard to ignore. What nobody declares is inevitability. A weak patch can deepen without spreading. A pole can sprint, kink, and slow. But these anomalies are the field's loudest messages that core geometry is changing now. If the eastern minimum continues to intensify and reverse flux under southern Africa links westward, the weak field belt could widen into South America, raising satellite exposure over new longitudes. If high-latitude lobes keep favoring Siberia, the pole's heading will keep drifting faster for a while, with practical consequences for navigation models. This is the operational edge. A quiet, coordinated nudge from the ground network can warn that the SAA footprint is about to shift, buying weeks to move uploads and high-voltage modes. A rising instability score for high-latitude secular variation can justify an interim magnetic model release before era budgets blow up. The anomalies aren't trivia, they're the scoreboard. And right now, the numbers say the game is still on. Quantum Sensing 101, why these devices hear the unhearable. So what actually heard the shift before satellites drew it clean? Start with atoms. In a warm glass cell, alkali atoms like rubidium align their spins when you shine the right laser light. Nudge that alignment with a magnetic field, and the spins precess at a frequency set by fundamental energy gaps. Read that precession optically, and you've built an atomic magnetometer. Because the ruler is quantum, an atomic transition, you get absolute measurements with vanishing drift. With spin exchange relaxation, free tricks, and lock-in detection, sensitivity drops into femtotesla territory. That's a millionth of a billionth of a Tesla, small enough to chase the core's slow breath. Diamond takes a different path. Swap one carbon for nitrogen and leave a neighboring vacancy. That defect is an NV center. Hit it with green light, drive microwaves across its spin levels, and watch the fluorescence dip where the magnetic field shifts the energy splitting. The result is a room temperature quantum compass on a chip. Pattern many NVs, and you've got a magnetic camera that sees gradients at micrometer scales, with 4 crystallographic orientations letting you reconstruct the full vector. They're tough, compact, and steady for long averages, which is the key for teasing out interannual drifts. If you want the sensitivity crown, you cool down. A SQUID, superconducting quantum interference device, uses phase coherence around a superconducting loop. Tiny changes in magnetic flux shift the interference pattern, which you read as voltage. Cryogenics is a hassle, but in shielded labs, SQUIDs resolve fields so faint they make most signals look loud. In practice, field teams mix and match. Atomic cells for absolute long-term baselines, NV arrays for vector detail and gradients, SQUIDs for reference truth and control conditions. But raw sensitivity isn't enough. The world is noisy. Cars, elevators, rail lines, power harmonics, even your heartbeat. So arrays go differential. Put 2 sensors close together, subtract their readings. Far-field junk cancels, local gradients survive. Scale that up to gradiometer networks, dozens to hundreds of stations with synchronized clocks across cities, countries, and oceans. Now you can cross-correlate. If a wiggle shows up across stations with lags that match Earth's rotation rather than local time, you're not hearing a train. You're hearing something deep turning under you.
Quantum helps three ways. First, coherence. Spins or superconducting phases evolve predictably, so you can
average for hours to weeks without washing out the signal you care about. Second, absolutes. Atoms and NV centers define their own yardsticks, so drift, the enemy of long-term monitoring, stays low. Third, clean readout. Optical detection and modulation schemes push you to shot noise limits, below the technical noise that plagues coils and flux gates over months. Here's how that plugs into Earth's field. The core's changes at the surface are small, nanotesla and below, spread over months to years. The ionosphere and magnetosphere slap bigger, faster signals on top, with daily, seasonal, and storm signatures. To separate them, the network tags quiet intervals using indices like KP, AP, DST, and SIMH fits, and subtracts ring current and ionospheric contributions, and models induction in the crust using magnetotelluric conductivity maps. What survives, coherent at night across mid-latitudes, indifferent to solar local time, looks like secular variation's quicker cousin. Why not rely on classical magnetometers alone? Flux gates and coils are excellent for space weather and fast events, but their calibration drifts and 1F noise complicate month-to-year baselines at sub-nanotesla precision. You can beat that back with heroic engineering, yet atomic and NV systems start closer to the finish line. Absolute scale, low drift, and vector reconstruction with minimal recalibration. That matters when you're spotting a barely perceptible acceleration before the SAA redraws itself. Geometry is another edge. Static crustal magnetization muddies maps. Gradiometer configurations suppress static backgrounds and highlight changes. NV arrays can stare at the same spot and resolve local gradients, while triaxial atomic cells capture vector swings cleanly. Combined, they help distinguish a deep, smooth tug from a nearby switching cable at 8 a.m. Add accelerometers and thermistors, and you model out vibration and temperature fingerprints that would otherwise masquerade as field change. Fusion makes it useful. Satellites like Swarm and calibrated Cryosat-2 platform magnetometers see the field from above. Ground quantum arrays provide continuous, low-drift anchors below. Assimilation frameworks ingest both, respecting physics and estimate core flow a few years ahead. When the ground network's low-frequency residual thickens over the Atlantic-African sector, and satellites later map a reshaped South Atlantic footprint, that's not a prophecy. It's a pattern you can plan around. Fieldcraft turns theory into data. Teams bury cables, site stations away from rail lines and wind farms, and schedule night windows to dodge E-region currents. They run blind injections through pipelines to test for algorithmic pareidolia, co-deploy quantum and classical sensors for cross-checks, and publish residuals with filters and error bars so rivals can try to break the claims. They also multiplex, in atomic cells probing multiple transitions to triangulate vectors, in NV diamond reading all four orientations to reject axis bias. Redundancy kills false positives. The result isn't a siren, it's a heartbeat you can trust. A network of coherent references turns whispers into repeatable waveforms. When those waveforms grow thicker over key longitudes, you nudge operators, not reversal incoming, but conditions shifting. Satellite teams slide high voltage modes out of risky passes. Grid operators pre-stage for storm nights when a weak field belt sits overhead. Aviation planners rescore polar routes for dose. The science stays sober, the actions get earlier. That's the leap. Quantum coherence doesn't make the planet louder, it makes us better listeners. And in a system where timing between waves and flux patches sets the mood, better listening buys lead time. The first odd signals, quiet whispers that didn't fit. The first hint didn't arrive with sirens. It crept in during those post-midnight windows when ionospheric currents nap and campuses go quiet. A handful of atomic stations, oceans apart, logged an ultra-low frequency sway, periods stretching over weeks to months, amplitudes well under a nanotesla. Alone, each trace looked like a shrug. Correct, for longitude and stacked them, and the waveforms nodded, in time like distant metronomes sharing a wall. They tried the usual suspects first. Seasonal fingerprints tied to thermospheric winds and solar EUV, removed with annual and semi-annual fits. Daily cycles, scrubbed using quiet day curves, KP and AP thresholds, and SYH cuts. The residual stayed clearest at night, most coherent at mid-latitudes, and stubborn through solar lulls. If this was space weather, it had a strange sense of schedule. Then a smaller oddity surfaced near storm days.
Hours before moderate disturbances, a few stations reported faint, phase-coherent ripples. Pre-event quivers too small for operations, too consistent to ignore. Normally, the magnetosphere sings after the hit, not before. Cross-correlations showed phase lags that didn't match.
Known ionospheric sources. The arrows pointed down. Skeptics took the wheel. Teams shoved sensors into metal shields, ran cryogenic squids next to atomic cells, and co-deployed classical flux gates as referees. They blinded the pipelines with synthetic injections to catch algorithmic daydreaming, dithered temperatures, rattled mounts, and parked trucks and generators near test sites on purpose. If a trick could fake the signal, they wanted it found in-house. The quantum arrays kept agreeing, with themselves, with each other, and with satellite data on the big swings. Then kept seeing a faint basement the classical gear barely resolved. Collocations told the story cleanly. At shared observatories, atomic magnetometers and NV diamond gradiometers tracked diurnal responses and storm dynamics in step with flux gates. After modeling and subtracting ring, current, and ionospheric contributions using DES-T, SYH, and regional conductivity maps, the quantum unit still held a coherent sub-nanotesla sway. This wasn't raw sensitivity alone. It was stability, an absolute scale, letting averages run long without drifting off the trail. One detail raised eyebrows. Stations thousands of kilometers apart showed residuals with similar shapes once you accounted for longitude. The lags matched rotation, not local time. Meanwhile, sites near rail lines or wind farms were the dirty controls. Their extra clutter didn't project into the coherent component. It stayed local and spiky. The signal of interest rode under that, smooth and slow. Unknown to some ground teams, satellite analysts were nursing their own puzzle. Night-side low-latitude passes from SWARM and calibrated platform magnetometers on Cryosat-2 showed secular variation wiggles that resisted external field explanations. When they downweighted high-latitude segments and emphasized quiet intervals, an interannual texture emerged with regional peaks over the Atlantic-African sector and the Western Pacific. When the ground network and the satellite group finally swapped notes, the fingerprints overlapped enough to justify late-night pizza and more tests. Crustal induction was a fair challenge. Time-varying external fields drive geoelectric currents, which throw secondary magnetic signals back at the surface. Teams pull 1D and 3D magnetotelluric conductivity models, simulated induced responses to measured external drivers, and subtracted them. The residuals didn't hug coastlines or conductivity contrasts. They traced broad belts that line up with westward drifting flux corridors and the route of the South Atlantic Anomaly. Timing added intrigue. In the months before the Eastern SAA minimum deepened, mid-latitude stations ringing the South Atlantic logged a subtle growth in the low-frequency residual. No step, no trumpet, just a thickening heartbeat. After satellites mapped the reshaped footprint, the amplitude eased. Up north, nightside stations under the pole's sprint path recorded small phase flips consistent with shifts in the tug-of-war between Canadian and Siberian high-latitude lobes. Not perfect alignment, close enough to matter. It stress-tested everything. Leave one out arrays. Drop a station. Does coherence collapse? It didn't. Randomized time windows. Correlations faded as they should, then returned with proper alignment. Rotate coordinate frames, split vector components, change filters and baselines, swap software stacks between labs. No single processing choice conjured or killed the signal. Publishing residuals and filters invited rivals to take shots. The pattern held under hostile code. Phase became the decider. If the source is deep and rotates with Earth, two mid-latitude stations at different longitudes should see the same waveform offset by the rotation time between them. They measured those lags. The offsets match rotation, not sunrise. Nightside Europe and nightside South America, each in their own midnight, preserved coherence. Meanwhile, superposed epochs around hundreds of storms showed only a weak, broad preamble. Too mushy to explain the phase-stable drift that ran through quiet weeks. What remained behaved like secular variation's quickened cousin, interannual and multi-year undulations, strongest over the Atlantic-African sector and certain Pacific longitudes, nightside stable, mostly indifferent to solar local time. The amplitude sat in the sub-nanotesla basement, yet it showed up across instruments, arrays, and pipelines. It looked like the planet speaking softly. No one called it a countdown clock. Torsional waves and magneto-Coriolis modes
can hum without lighting up the scoreboard. Flux patches can pass like ships in fog. But the logic was tight. If deep waves modulate shear, where reverse patches graze, the surface should breathe a little before geometry changes appear in standard models. That breath is what the network seemed to catch. The practical move was simple. Keep a rolling baseline. Watch for thickening in key sectors. When the
Low-frequency floor rises and phase lines up with expected wave transits, ping the modelers and the operators. Not flip incoming, but conditions shifting. Then see if satellites confirm with a shape change and update the playbook. The quiet signals didn't shout. They tapped the glass. Just loud enough for anyone listening closely to turn their head. Separating sky from stone, filtering out space weather. If the whisper is real, it has to walk through the sun's noise without changing its shoes. So the team started with quiet. They flagged nights when KP and AP sat low. SYH was flat, and auroral electrojets relaxed. They carved post-midnight windows where E-region currents fade and thermospheric winds settle. If the signals were space weather in disguise, this should have erased them. It didn't. The residual heartbeat stayed, small, coherent, and most visible at mid-latitudes under calm skies. Next came the ring current, the bruiser that drags the field down during storms. Analysts modeled and subtracted its contribution using DST and SYH, tuned transfer functions station by station, and cross-checked with GOES pressure jumps. The residuals survived, especially on the night side away from auroral influence. That asymmetry mattered. External current systems tend to track the sun's clock. The whisper didn't care about sunrise. Auroral contamination is the classic scapegoat. The array was split deliberately. High-latitude stations doubled as controls. Mid-latitude and equatorial sites were the testbed. During auroral activations, the polar stations flared in step with electrojets. Mid-latitudes followed the known playbook, then calmed. The stubborn low-frequency drift showed up strongest where auroral fingerprints were weakest. That knocked a big suspect off the list. Diurnal structure can hide in small phase slips, so they stack thousands of days into superposed epochs aligned by local solar time. Anything tied to the sun's rhythm builds. Anything indifferent washes out. The quiet residuals refused to lock to dawn or dusk. Instead, they slid with longitude in a way that matched rotation, not local time. Two stations separated by 60 degrees of longitude saw the same wave with a lag consistent with Earth turning beneath a deep source. The ionosphere doesn't just carry current, it changes character. Teams pulled GPS, derived total electron content maps, and C2per forecasts, tagging nights when TEC was unusually placid. They also watched D-region absorption proxies to catch odd proton events. On the clearest nights, the residuals remained. Crustal induction was trickier. Space weather has a voice. The whisper wasn't singing along. External fields drive geoelectric currents that echo back as secondary magnetic signals. The fix was forward modeling. Using regional 3D magnetotelluric conductivity models where available, and 1D where necessary, they simulated induced responses to the measured external drivers, then subtracted those from the records. If induction were to blame, residuals would hug coastlines, conductivity contrasts, or known anisotropy. They didn't. The coherent floor traced broad belts that align with westward drifting core flux corridors and the South Atlantic root zone. They tried to break the result. Swap a 1D conductivity model for a 3D block. Does the pattern flip? It didn't. Tighten and loosen bandpass windows. Do you conjure coherence? The amplitude wobbled within error bars, but the phase structure held. Change quiet day definitions. Does it vanish? It dimmed in some windows, then reappeared under alternative indices. Rotate coordinate frames, split vector components, and reprocess with independent codebases. No single choice created or erased the signal. Phase tests sealed it. If the source rotates with Earth, two mid-latitude stations at different longitudes should see similar waveforms offset by the rotation time between them. They measured those offsets. They matched rotation, not solar local time. Nightside Europe and nightside South America, each in its own midnight, preserved coherence. Meanwhile, when they aligned hundreds of storm onsets and looked for a common prelude, they found only a broad, weak sigh, too mushy to explain a phase-stable drift that persisted through quiet weeks. Environmental clutter was the last refuge of doubt.
They mapped rail schedules, wind farm outputs, and industrial cycles. They attached accelerometers to mounts and thermistors to housings. Cultural noise left sharp spectral lines or rigid schedules. The whisper lived below that, broadband and slow. Sites beside rail lines served as dirty controls. Their local spikes didn't project into the array-wide coherent component. They stayed put while the residual of interest slid with longitude. Satellites played referee. Analysts leaned on night-side, low-latitude passes from Swarm, added calibrated platform magnetometers from Cryosat-2, and enforced strict external field models. They focused on secular acceleration, the second-time derivative that highlights rapid core dynamics. Interannual wiggles with similar periods and regional weighting emerged, strongest over the Atlantic African sector and parts of the Western Pacific. Not identical to the ground traces. Altitude and filters matter, but close enough to argue a shared source under different vantage points.
One clever cross-check tested causality claims. Those faint pre-event ripples seen before some disturbances could have been magnetospheric breathing. So they randomized onset times, reran superposed epochs, and watched coherence collapse on demand. Aligned by the residuals phase instead, and coherence strengthened. The sky obeyed the sun. The stone obeyed rotation and geography. After months of subtracting, modeling, and trying to break their own work, what remained was a cleaner silhouette. Interannual and multi-year undulations, sub-nanotesla in amplitude, night-side stable at mid-latitudes, indifferent to solar local time, and strongest over sectors linked to known core features. It looked like secular variations' quickened cousin, not a trick of the ionosphere, ring current, or rails. Nobody claimed prophecy. They claimed a fingerprint. Fence the sky in, and the planet's interior still leaves a trace you can measure, compare, and watch for change. With that fence built, the next question turns inward. What flows, waves, and patch encounters in the core could be breathing this signal into the surface field right now? Inside the flow, what core simulations predict? With the sky fenced off, we turn the models loose and ask the core to explain itself. Data assimilative Geodynamo runs start from what we actually measure, observatory records and satellite field maps, and nudge a physics-based core into agreement. It's weather forecasting for molten iron, imperfect parameters, honest uncertainties, and a short, useful horizon. They converge on the same trouble spot. Beneath southern Africa, reverse polarity flux patches sit at the core mantle boundary and drift west. In runs that mirror satellite secular acceleration maps, those negative lobes undercut the dipole above the South Atlantic, matching the weak belt satellites cross every day. That's the structural piece. The dynamic piece is waves, axis-symmetric, torsional Alfvén pulses with subdecadal periods, roughly 6-year trains, plus tilted magneto-Coriolis modes. The waves don't flip the field, they modulate shear, altering how patches meet, merge, or miss. Now layer the mantle on top. The core mantle boundary leaks heat unevenly. Subducted slabs cool some longitudes, hot plumes warm others. In the code, that patchwork acts like a textured ceiling that shepherds flow into corridors. Westward drift appears naturally in certain belts, and reverse flux tends to survive under the Atlantic African sector. When you let waves run through that landscape, the South Atlantic Anomaly split emerges. One western minimum that creeps west at about 0.2 to 0.3 degrees per year, and an eastern minimum near southern Africa that deepens faster with little east-west motion. That asymmetry matches recent satellite field models. Sensitivity is the headline. In ensembles, same physics, slightly different initial states. Some realizations flirt with excursions, others wobble and stabilize, and a few push the dipole weaker for longer. The difference is timing. Whether a waves phase arrives when two patches are about to shear, whether reversed flux bridges across longitudes, whether the mantle's ceiling lines up to keep the corridor open, arrive in phase and you amplify, arrive offbeat and you damp. So what fingerprints separate futures? In runs that lean excursion or reversal, reversed flux bridges don't just sit under southern Africa. They elongate and connect towards South America, broadening the surface weak field belt beyond a single pit. Before that geometry fully shows upstairs, the simulations throw off localized bursts of secular acceleration, short-lived spikes in the second-time derivative over the Atlantic African sector, and at times the Western Pacific. Those bursts look a lot like the thickening basement, the ground network flagged ahead of recent SAA reshaping.
The North Magnetic Pole sprint plays by the same rules. High latitude flux lobes beneath Canada and Siberia trade strength. When the Siberian lobe bulks up, assimilative runs send the pole racing that way. When the Canadian side fights back, the path kinks or stalls. Tilted magneto, Coriolis modes can bias which lobe gets help for a few years. That matches the real-world pattern. Fast drift, brief pauses, then another lurch.
Forecast windows are short. Push the assimilation forward a few years and you get a probabilistic roadmap. Likely westward motion of that western minimum, odds that the eastern pit deepens. Windows when wave trains will cross the Atlantic corridor in phase with expected patch encounters. Beyond that, errors multiply. But for operators, a few years is actionable, enough to adjust satellite operations, plan grid training around storm seasons, and schedule interim magnetic model releases before error budgets blow up. There's another coupling the code can't ignore: angular momentum exchange. Torsional waves move momentum along cylinders, and magnetic torques can couple the outer core, inner core, mantle. Some frameworks allow a whisper of inner core rotation variability. Shift that phase, and you nudge when the next wavefront hits a corridor. It's subtle, but in a system where timing runs the show, subtle counts. We also test geography. The Atlantic African sector isn't alone. Assimilation runs sometimes light up belts over the Western Pacific and under parts of the Indian Ocean. When those belts and the Atlantic corridor pulse together, ensembles show a higher chance of broader dipole weakening. The ground network's low-frequency residuals have shown coordinated thickening in some of those longitudes during certain years. Not proof, consistency that earns a longer look. What would count as a live heads-up inside the models? 3 conditions stacking. Sustained growth of reverse flux under southern Africa with bridges reaching west, a train of torsional waves timed to boost shear at those encounters, and a widening weak field belt in satellite maps, not just deepening pits. Hit those for a few years, and probabilities tilt toward an excursion-like episode. Miss one, and stabilization regains ground. Humility is baked in. These models run far from true Earth-like viscosity and magnetic Reynolds numbers. They're approximations guided by data. Yet when they reproduce travel times for torsional waves that match independent core field strength estimates, and when they predict SAA reshaping that satellites later confirm, they've earned a seat at the table. The trick is to keep the loop tight. Sensors nudge models, models predict short horizon features, satellites check, and the network listens harder where the code says the next whisper should rise. That's the through line. The core story isn't a single plot twist. It's choreography. Waves as metronomes, patches as dancers, the mantle as stage. When they line up, the surface field breathes faster. The models show how that breath should look. The sensors tell us when it starts. The candidate mechanisms, torsional waves, flux patches, and a ticking clock. Here's the working picture at street level. The outer core organizes into nested cylinders by rotation. Every so often, a torsional Alfvén wave runs along those cylinders. An acceleration pulse that speeds up and slows down entire bands of liquid iron. The pulse moves at a speed set by magnetic tension and density, which is why its subdecadal period tells us something about the core's average internal field strength. On its own, a wave is background music. Put it near the right structures, and it starts keeping time for the dance. Those structures are flux patches hugging the core mantle boundary. Think concentrated regions of magnetic field, the building blocks of the large-scale pattern we see at the surface. Some patches align with the dipole, others are reversed. Under southern Africa, reverse patches are the repeat offenders. They drift west along corridors carved by patchy heat flow through the boundary. When 2 patches approach, the flow between them shears and stretches field lines. Sometimes they pass quietly. Sometimes they reconnect and rearrange geometry that echoes upward to the surface. The clock appears when a torsional wave and a looming encounter meet on time. If the wavefront arrives when 2 patches are within striking distance, it boosts the local shear. That extra shove makes reconnection and reorganization more likely. Arrive out of phase, and the wave dampens the interaction. Timing doesn't create patches, but it decides which meetings matter. That's the ticking in the countdown metaphor. Not seconds, but opportunities. We test this with phase. Assimilation runs infer the position and phase of wave trains. Ground arrays and satellites track where secular acceleration, those short bursts in the second derivative, lights up. When a modeled wavefront crosses the Atlantic African corridor and ground residuals thicken there for months, we're seeing timing line up. A season later,
Satellite maps sometimes show the SAA footprint adjust. The eastern minimum deepens or the western lobe creeps and reshapes. Not every crossing pays off. Enough have to make the pattern hard to shrug off. Westward drift sets the stage. Non-zonal flow pushes patches along at a few tenths of a degree per year. That conveyor brings reverse flux from the African sector towards South America, where it can knit into longer bridges that undercut the dipole more broadly. In the code, the West African margin behaves like a gate. Reverse flux that clears the gate tends to seed wider weak field belts. In data, the western SAA minimum keeps edging west while the eastern pit deepens faster with little zonal motion, exactly the asymmetry you'd expect if two corridors carry different loads at different times. There's a second set of rhythms, magneto-Coriolis modes, that tilt and precess. These aren't purely torsional. They redistribute flow in patterns that can advantage one hemisphere or longitude band. When high latitude,
Lobes near Siberia get help from a tilted mode. The North Magnetic Pole sprints that way. And ground stations under its path log small phase flips. When the Canadian side takes a turn, the sprint kinks or slows. This isn't a contradiction. It's the same coupling story playing out at different latitudes with different actors. So what rises to the level of a credible precursor? Three pieces moving together. 1. Sustained growth and elongation of reverse flux bridges beneath southern Africa, extending towards South America in assimilation maps. Not a single season's flicker. 2. A train of torsional wave passages timed by phase estimates to amplify shear at those encounters. 3. A widening weak field belt at satellite altitude beyond a deepening pit, mirrored on the ground by a thickening low-frequency residual across multiple longitudes. Hit all three for a few years, and the odds tilt toward excursion-like behavior rather than a quiet stabilization. False starts are part of the deal. Waves arrive in trains. Not every car meets a crossing. Patches can diffuse or get diverted by local flow before they matter. Phase estimates carry error bars because the core's parameters aren't directly measured. That's why the countdown isn't a timer, it's a likelihood meter. When two dials turn and stay turned, operators change posture. Satellites slide high voltage modes out of the expanding corridor. Grid planners rehearse storm playbooks under updated geoelectric maps. Navigation agencies consider an interim model release. There's also the mantle, the stage that never leaves. Heat flow heterogeneity fixes the corridors, biases where flux survives, and shapes how waves express at the boundary. Put the same torsional pulse under two ceiling textures, and the surface signature differs. That's why the Atlantic sector keeps starring, while other longitudes pulse in and out. It also explains the SAA split. Two neighboring corridors carry reverse flux on slightly different schedules, so one minimum can deepen while the other drifts. Here's the human readout. When the low-frequency floor over the Atlantic-African belt thickens and phase lines up with the predicted wave transit, satellite operators bump their SAA risk score for the next season. After a couple of those runs, if satellites also map a broadening weak field swath, planners stop treating it as noise. They reroute sensitive tasks, stash gain changes in safer longitudes, and pad lifetimes with procedures rather than hardware. It's quiet, boring resilience. And it works. So the mechanism isn't mystique, it's choreography. Waves keep time, patches do the steps, the mantle sets the lanes, quantum networks are the metronome in the pit, steady enough to tell when the tempo changes just before the dancers hit the mark. That's the countdown worth listening to. Earth's memory, paleomagnetism, and lessons from past flips. To see whether today's whispers have a history, we ask rocks that cooled before humans had calendars. Lava flows freeze the field's direction and strength as they pass through the Curie point. Fine sediments, settling grain by grain, align tiny magnetic particles with the ambient field and lock that bias as they compact. Each record is a snapshot, stitched across sites and dated with radiometric clocks, ash layers, or ice core tie points. They become a patchwork album of the Geodynamo's moods. Open that album and flips aren't rare exceptions. The Brunhes-Matuyama reversal sits about 780,000 years ago, captured in lavas from the Atlantic to the Pacific. Older chapters show the Matuyama-Gauss reversal near 2.58 million years. Between full flips, shorter excursions pepper the record. The La Champ excursion, roughly 41,000 years ago, is the standout. Intensity plunged, direction swung wildly at some sites, then the field recovered to the same polarity within a few centuries to a couple thousand years depending on resolution. Ice cores back it up. Cosmogenic beryllium-10 spiked as shielding weakened,
an independent marker that more cosmic rays punched into the atmosphere when the field sagged. Fieldwork behind those points is gritty. Teams hike to basalt cliffs, drill oriented core plugs, and run them through heating cycles to peel away later overprints until the primary magnetization emerges. For sediments, alternating fields nudge secondary signals aside, revealing the older imprint. Every sample comes with caveats. Chemical changes can rewrite the tape. Sedimentation smears time over decades to centuries. That's why compilations matter. Global stacks average local quirks and give us confidence in broad timing, not day-by-day details. What patterns jump out? First, the field strength ebbs and flows across millennia. When the axial dipole weakens, non-dipole structure blossoms and directions grow noisy. Full reversals unfold over thousands of years. A drawn-out weakening, directional wanderings that sometimes leap, and a rebuild on the other side. Excursions
are shorter, patchier, and asymmetrical across the globe. Some regions see 180-degree swings, while others drift modestly. The shared trait is low intensity. Weakness breeds complexity. Do we see cousins of today's South Atlantic behavior in these records? We see recurring low-intensity zones over the Atlantic-African sector at various times in the Holocene reconstructions, and hints of westward drifting anomalies traced back through archaeomagnetic and volcanic data. Recent modeling of Holocene field evolution suggests structures similar to the present South Atlantic Anomaly appeared near the Indian Ocean over a millennium ago and drifted west, feeding today's configuration. That doesn't prove fate. It puts modern weakness in a long lineage of Atlantic-centric soft spots. There's a timing lesson. The present-day average decline of the dipole, about 16 nanotesla per year over the last 180 years, looks fast on human scales, but in paleomagnetic terms, it's a gentle slope stacked on interludes, where intensity either steadied or rebounded. Flips don't follow a metronome. Some intervals between reversals stretch tens of millions of years, others bunch closely. The engine has modes, not a clock. The last amp carries a practical warning. You can crater shielding without a global compass flip. During that episode, cosmogenic isotopes screamed weak field, while directional changes varied wildly by site. In today's terms, that's a world where satellites and high-altitude flyers feel more radiation for a few solar cycles, grids stay on their toes during storms, and migration maps blur without the drama of north becoming south everywhere. The stakes we've been outlining live in that space. Dating remains the soft edge. Lava flows give crisp directions but sporadic timestamps. Sediments give continuity but smear. Age models can differ by centuries to millennia across sites. Way-like wiggles at interannual scales simply vanish into the averaging. That's why live sensing matters. Paleomagnetism tells us what kinds of chapters exist. Quantum networks and satellites tell us which page we're on. Even with those gaps, paleo data sketch signatures that echo our sensors' hints. Before and during reversals or excursions, secular acceleration, fast changes layered on slow drift, spikes and bursts. Low-intensity belts widen beyond a single pit. Virtual geomagnetic poles wander more quickly, especially along preferred longitudes. In Holocene stacks, the Atlantic sector shows repeated softening paired with westward drifting features. Today, we see a split South Atlantic anomaly with a western lobe creeping west and an eastern lobe deepening. Perfectly plausible descendants of that behavior. One more thread is mantle influence. Long-lived heat flow heterogeneity at the core mantle boundary should leave persistent fingerprints in where weak belts prefer to sit. Paleolongitude distributions of virtual poles and intensity lows suggest fixed corridors that the dynamo revisits. That rhyme gives confidence when models point to corridor-guided flux under southern Africa, feeding modern weakness. So Earth's memory answers two emotional questions. Are we in uncharted waters? No. Weak field belts, fast pole drift, and regional chaos have played before. Do we get a schedule? No. The last time the field truly flipped, no one was around to measure the lead up at nanotesla precision. The best move is to pair the album with the live stream. Use rocks to recognize the patterns, and use quantum-anchored networks and satellites to watch them form in real time. That turns an old story into a forecast we can actually act on. Real-world stakes: satellites, grids, navigation, and biology. Here's where a quiet nanotesla becomes a budget line. Start in orbit. In weak field zones like the South Atlantic, radiation belts sag closer to low Earth orbit. That means more high-energy particles threading spacecraft. Memory bits flip, detectors spike, star trackers lose lock. Operators already live with this. They draw SAA boxes on orbital maps, step instruments down, and schedule uploads elsewhere. A few percent more exposure year after year shortens mission life unless you compensate. Heavier shielding, smarter scheduling, and firmware that can take a punch. Space weather stacks on top.
A storm swells the ring current and compresses the magnetopause. If that lands over a chronically weak corridor, hits go up, more single event upsets, more latch ups, and more safe mode triggers right where you least want them. So the planning shifts. Teams now cross-reference solar forecasts with geographic risk. If the ground network signals the weak field belt widening west into new longitudes, they slide high voltage modes out of those passes. Stash detector gain changes in safer arcs and pad autonomy to ride through spikes. A few timely reroutes can save days of mission life per satellite across a season. On the ground, it's not particles, it's currents. Fast magnetic swings induce geoelectric fields. Long conductors, transmission lines, pipelines, transformer neutrals act like antennas. Geomagnetically induced currents bias transformer cores, push them toward half-cycle saturation, and pump harmonics back into the grid. The result is reactive power swings, misbehaving protection, and in bad cases, overheated hardware. Quebec 1989 is the famous example. It's not the only one. Utilities now stand up, monitors, storm playbooks, and regional geoelectric models. A wider weak field belt shifts those models' inputs. The same solar punch induces stronger fields where shielding is soft. If the belt creeps under a major interconnect, operators can pre-stage, limit long-distance transfers, increase reserves, watch GIC meters, and configure networks to shorten effective conductor lengths. It's not drama, it's prevention. Aviation feels the shield in two places, dose and comms. Polar routes shave time but ride under auroral activity. During events, airlines already reroute to manage dose and keep HF radios talking. A weaker magnetic baseline nudges ambient counts at cruise a bit higher, especially at high latitudes, and shrinks margins during storms. The fix is planning. Dispatchers fold weak field maps into the same dashboard as solar particle alerts and jet stream winds. When two dials turn, storm risk and an expanded exposure belt, they adjust routes early rather than mid-flight. Flight surgeons update dose calculators for crews stacked on polar legs that week. Navigation is the quiet grind. Compasses aren't antiques. They backstop drilling rigs, survey teams, and small aircraft. Directional drilling depends on magnetic models to steer underground. When secular variation speeds up along the pole's sprint path or across active corridors, those models age out faster. Firms reprocess surveys and push more frequent updates to rigs. Aviation needs current magnetic declination for headings and procedures. The World Magnetic Model's 5-year rhythm now includes interim releases when drift outruns tolerances. With a live stability score from the ground network, agencies can decide when to push an early update before errors stack. Animals navigate through this landscape without dashboards. Birds read inclination for direction and intensity gradients for position, likely with cryptochrome chemistry and magnetite working different jobs. Sea turtles, sharks, and salmon show magnetic map use too. When contours shift, maps blur. Most species hedge, stars, odors, landmarks, so migration doesn't collapse, it smears. Detours lengthen, arrivals spread. Fisheries managers care because timing ripples through food webs. Early notice of where contours will change most lets conservation teams protect alternate stopovers and adjust seasonal closures with a bit more foresight. Humans don't sense nanotesla swings directly. Claims that everyday geomagnetic wiggles drive mood or cognition outpace evidence. The biomedical stake you can measure is radiation dose at altitude and in near space. That's why astronauts and frequent polar flyers sit in the practical risk column. A weaker field bumps dose planning, not panic. For everyone else, the effects arrive as downstream reliability. Fewer satellite outages during a stormy week because uploads moved, fewer grid alarms because transformers were debiased, fewer last-minute polar reroutes because the risk model flipped to amber days earlier. The compounding risk sits at intersections. Picture a moderate storm hitting while the South Atlantic belt has expanded into South America. Satellites see more upsets, ground systems sit under stronger.
Induced fields and polar routes face tighter dose margins at the same time. No single factor guarantees failure. Together, they squeeze operational slack. That's why the whisper matters. A rolling, low-frequency baseline that thickens over key sectors gives operators a heads up before the squeeze arrives. Translate that into moves. Satellite teams widen SAA avoidance zones and rehearse safe mode thresholds keyed to geography. Not just KP utilities, stage crews. Retune protection for harmonics and hold more reactive power near suspect corridors during storm windows. Aviation planners keep a few extra non-polar pairings on the board when indices rise.
Drillers subscribe to interim magnetic updates and tighten error budgets in fast-changing regions. None of this requires a prediction of reversal. It needs honest odds that the playing field is tilting now. That's the promise of listening hard. Quantum-anchored networks don't shout dates. They buy hours to months of lead time. Turn that into checklists, and nanotesla whispers turn into tangible resilience. From curiosity to utility. Forecasting with quantum networks. What do you do with a whisper you can trust? You wire the planet to hear it in real time. Picture a tiered net. Absolute atomic magnetometers anchoring national observatories, NV diamond gradiometers on quiet campuses and coastal labs, a few shielded squid references, and ocean bottom nodes filling blue gaps far from cultural noise. Each station runs a tight clock. Together, they form a coherent ear tuned to Earth's low notes. The value isn't raw sensitivity, it's fusion with physics. Ground arrays listen continuously. Satellites, swarm now, plus calibrated platform magnetometers like Cryosat-2 sweep from above. Ocean bottom stations dodge city hum. A shared pipeline ingests all three with open metadata, time tags, and uncertainty bars. External sources get fenced in first. Ionosphere, and ring current modeled with KP, AP, DS, SYH, and assimilative electrodynamics. Induced crustal signals removed using regional 3D conductivity maps. What survives is the slow interior component we care about. Forecasting looks different here. No icons, no 7-day maps, just indices tied to mechanisms and regions. One index tracks interannual secular acceleration over the Atlantic-African belt, derived from ground residuals and satellite secular acceleration. Another tracks torsional wave phase, estimated from assimilation runs constrained by satellite data. A third measures weak field belt width at satellite altitude, not just depth at a single minimum. When two dials push past threshold and stay there, the system flips from green to amber for that sector. Conditions favorable for geometry change within months to a few years. Machine learning helps, but it doesn't fly blind. Models train on physics-guided features, phase, drift rates, longitudinal weighting, rather than raw squiggles. They learn which combinations preceded SAA reshaping or North Pole sprint surges, and when similar patterns fizzled. Outputs are probabilities with error bars. Higher than baseline odds that the weak field corridor will widen west, moderate likelihood that high-latitude secular variation will outpace the world magnetic model's comfort window, low odds of a broad lull. Operators translate those odds into schedules. Satellite teams treat amber like weather, slide high voltage modes out of flagged longitudes, shift detector gain changes to safer arcs, and tighten autonomy during risky passes. Constellations reroute calibration maneuvers. Big observatories avoid firmware uploads inside the belt. Over a season, that routing saves days of mission life and dodges the unlucky safe mode during the storm. Utilities link the signal to storm playbooks. Solar alerts drive most of the risk, but the same storm over a softened corridor induces stronger geoelectric fields. When the net says the belt has widened into new longitudes, operators pre-stage, cap long-distance transfers, bring extra reactive power online, arm GIC monitors, and adjust transformer loading to reduce half-cycle saturation. It's the difference between a rough night and a cascading outage. Aviation folds the indices into dose and comms dashboards. Dispatchers already juggle jet streams and solar particle alerts. Add a weak field exposure map, and polar routes get nudged earlier when two dials turn. HF Comms backup plans rise on checklists. Flight surgeons tweak crew dose calculators for the week. Passengers don't see the chessboard. The ops room feels the margin. Navigation agencies watch a stability score for high-latitude secular variation. If drift outruns tolerances, they release an interim magnetic model before 5 years are up, avoiding creeping errors in drilling, surveying, and small aircraft headings. Drillers subscribe to region-specific stability flags and tighten error budgets in fast-changing corridors, cutting rework downhole. Trust rides on transparency. The network
Publishes residuals, filters, and uncertainty models in near real time. Amber periods that don't pan out get postmortems. Thresholds were too tight, phase estimates lagged, or external models leaked noise. Those failures refine the dials and keep countdown from becoming clickbait. Coverage expands by cooperation. National observatories share low latency streams. Universities host NV arrays. Space agencies release prompt field solutions. Research vessels drop ocean bottom nodes along shipping lanes. Utilities and airlines fund edge stations where decisions depend on the dials.
In return, they get tailored risk products and open archives. The budget case is simple. Cheaper than a single transformer replacement, cheaper than a lost instrument after a bad SAA pass. None of this calls a reversal. It calls changing odds with enough lead time to move, hours to shift and upload, days to reconfigure a substation, weeks to reroute flights for a stormy season, months to ship an interim model. The whisper becomes a workflow. The map stops being wallpaper and turns into a live display, where the deep engine's slow breath is a signal you can act on before it becomes a headline. The human and animal angle, magnetoreception and everyday life. We've been listening to machines. Now listen to the creatures that navigate inside this shifting map. Birds first. Night migrants like European robins hold two magnetic tools. For direction, they read inclination, the tilt of field lines, through chemistry in the eye. A light-sensitive protein, cryptochrome, forms radical pairs whose spin states evolve in ways the visual system can detect under blue light. That's the compass. Angle, not true north. For location, many species likely use magnetite particles as intensity sensors, giving them a faint map tied to field strength. Two sensors, two jobs. Redundancy keeps them flying when one cue drifts. When the field's contours slide, the compass still points, but the map blurs. Migration routes kink, stopovers shift, and arrival windows spread. You don't see birds falling from the sky. You see flocks arrive days apart, or detour to a different bay when an intensity contour moves. Because they also follow stars, sun patterns, odors, and landmarks, they adapt, but not for free. Extra energy, tighter margins, and rougher timing for feeding and breeding. Sea turtles hatch and cross oceans, guided in part by magnetic signatures imprinted young. Salmon, sharks, and eels show magnetic map use too. As weak field belts widen or drift, those signatures move. Populations stretch routes or return to slightly different coastlines. For fisheries, that looks like timing shifts and change bycatch patterns. For conservation, it's a push to protect alternate stopovers and nursery areas when forecasts say the magnetic map will shift most over a season. Humans don't feel nanotesla shifts, but we ride their consequences. Pilots on polar routes weigh 3 dials now: jet streams, solar particle alerts, and weak field exposure along the path. A widening South Atlantic belt nudges dose models and HF comms risk, especially when storms loom. Dispatchers swap pairings early. Flight surgeons adjust accumulated dose budgets for crews stacked on high-latitude legs. Passengers never notice. The ops room avoids a scramble. On the ground, drilling rigs and survey teams still lean on magnetic models as a backstop. When the pole sprints or secular variation speeds up along a corridor, those models age faster. A foreman sees it as a few extra downhole corrections and a tighter error budget. Aviation needs current declination on charts. An interim world magnetic model release lands when drift outruns tolerances. That cadence now tracks the same live indices we've been following. There's a quieter biomedical subplot that attracts noise online. Do everyday geomagnetic wiggles swing mood or sleep? Evidence is mixed and often confounded by light, schedules, and weather. If an effect exists, it's small beside those variables. The hard stake you can calculate is radiation dose for astronauts and high-altitude flyers. A weaker shield nudges dose up at crews more during events. That's planning, not panic. Route choices, duty cycles, and shielding assumptions updated when the risk dial turns. Here's the parallel that makes this feel less abstract. The same quantum coherence that lets a diamond defect hold a steady compass also shows up in a robin's eye as a faint orientation signal. Different scales, similar physics. It doesn't mean birds forecast reversals. It means when the field's geometry shifts, their sensory overlay shifts with it, and behavior follows next season. If early warnings say the South Atlantic belt will expand west into certain longitudes, wildlife managers can pre-position protections along alternate routes, just as satellite teams slide operations and grid operators stage crews. Culture meets science in how we communicate this. Not doom, but lead time. Communities.
Near new exposure longitudes, see more satellite outages during storms unless operators move uploads. Travelers on certain routes see longer flight times on rare days when polar legs get nudged. Fisheries adjust seasonal closures when migration timing spreads. Those are human-scale ripples of a core-scale change. So the everyday line is clear. Animals adapt, with costs spread over seasons. People plan, with costs moved from failure to preparation. A field that breathes faster doesn't rewrite life overnight, but it does tighten margins at intersections, space, sky, and sea, where decisions compound. That's why turning whispers into schedules matters. It gives birds a better map through protected stops, crews safer routes under active skies, and engineers a head start before the next storm arrives. Hype versus reality. What we know, what we don't. Let's draw the lines cleanly. Here's bedrock. Earth's magnetic field is forged by a liquid iron dynamo in the outer core, organized by rotation and buoyancy. Reversals and excursions aren't myths. Rocks and sediments record many, including the Brunhes-Matuyama reversal around 780,000 years ago, and the last Champ excursion about 41,000 years ago. Today, satellites and observatories agree the global dipole has weakened on average by roughly 16 nanotesla per year over the last 180 years, while the South Atlantic sector remains the standout weak zone. The North Magnetic Pole's recent sprint towards Siberia forced an early world magnetic model update before the normal 5-year cadence. We also know quantum sensors earned their keep. Atomic magnetometers, NV diamond devices, and squids anchor low-drift baselines and resolve sub-nanotesla, interannual signatures that classical instruments struggle to hold over months. In co-deployments, they match flux gates on diurnal and storm signals, and then keep tracking into a low-amplitude basement that remains after external fields are modeled out. Cross-checks with Swarm and calibrated Cryosat-2 platform magnetometers show consistent secular acceleration wiggles, strongest over the Atlantic African sector and parts of the Western Pacific. We know core dynamics can be fast on human timescales. Axiometric torsional Alfvén waves with subdecadal, roughly 6-year, periods have been identified from satellite and observatory data, and broader magneto-Coriolis modes help explain interannual changes. Data assimilative geodynamo frameworks, anchored to 180 years of surface and satellite field models, reconstruct flows and produce short-horizon forecasts that reproduce rapid secular variability features and travel times compatible with core field strengths. We know space weather stresses infrastructure. Storms induce quasi-DC currents in long conductors challenging grids. Satellites see more single-event upsets when belts swell. Aviation dose and HF comms risks rise on polar routes. Weak field belts don't cause storms, they raise exposure where storms hit. Now the guardrails. We don't have a date for a reversal or proof we're on that track. Simulations split across outcomes. Stabilization, excursion, like episodes, or long, uneven dips in dipole strength. The difference hinges on timing between waves and flux patch encounters, and on whether reverse flux builds bridges across longitudes. Forecast skill fades beyond a few years, because small errors at the core mantle boundary inflate quickly. That's why the countdown is a likelihood meter, not a clock. We don't know that the coherent, low-frequency residuals will always precede geometry changes. The pattern appeared before recent South Atlantic, reshaping and along the pole's sprint path, survived independent pipelines and matched satellite weighting. But precursor science is probabilistic. False alarms will happen, quiet seasons will too. Publishing residuals, filters, and negative results keeps the field honest. We don't know precise biological outcomes beyond radiation physics. Magnetoreception in birds, turtles, and fish has strong support. Cryptochrome-based radical pair chemistry for direction, likely magnetite for intensity. But translating subtle, regional field shifts into population-level impacts remains active work. For humans, everyday geomagnetic wiggles as a cause of mood or cognition changes lack robust evidence. The actionable health stake is dose at altitude and in space. Here's how we keep hype in check. Stick to verified signals. The SAA split into western and eastern minima, with the western lobe drifting west roughly 0.2 to 0.3 degrees per year, and the eastern lobe deepening faster with little zonal motion. The dipole's multi-decadal decline, interannual secular acceleration pulses over specific longitudes, torsional wave periods near 6 years. Anchor claims to open data, Swarm products, calibrated Cryosat-2 magnetometers, observatory records, and published assimilation outputs. Distinguish internal from external. Fence the ionosphere, ring current, and crustal induction with models and controls, then show what remains. Finally, clarity on stakes. A weaker field won't erase GPS, flip compasses overnight, or strip the atmosphere next year. GPS depends on timing and ionospheric models that adapt. Compasses drift by degrees over years. Interim WMM releases already address rapid changes. Atmospheric escape on these timelines isn't the concern. The real risks stack during storms over softened regions, exactly where early warnings pay off. So the reality is measured and useful. The core is restless. Sensors can now hear the low notes. Models can sketch short-term paths with uncertainty bars. The move isn't fear.
Its preparation tied to honest odds, transparent methods, and decisions that benefit from hours to years of lead time. Scenarios: slow flip, excursion, or
Stabilization. We fenced the sky and mapped the whispers. Now it's about posture. 3 paths make sense on human timelines, each with different costs and tells. Door 1 is the slow flip. The dipole keeps sliding for centuries to millennia, while non-dipole structure spreads. Reversed flux bridges beneath southern Africa lengthen toward South America, not just deepening 2 pits, but widening a belt. At satellite altitude, the weak zone sprawls beyond the South Atlantic box, turning narrow no-go lanes into wider corridors operators can't ignore. On the ground, the same storm induces stronger geoelectric fields over more longitudes, so utilities treat moderate KP days as higher risk when the belt sits overhead. Compasses don't spin, they drift faster. Enough that the world magnetic model needs interim, releases more often, and directional drilling budgets tighten. Airlines treat polar dose thresholds as hair trigger during solar seasons. The tells: a sustained, broadened weak field swath in satellite maps, multi-year growth of reversed flux bridges and assimilation runs, and a raised, steady floor in the ground network's low-frequency residual across the Atlantic-African sector and neighboring longitudes. If those stay aligned for years, probabilities lean toward a centuries-long reversal arc, not a date, a direction. Door 2 is the excursion. Think surge, not swap. The dipole strength drops hard for a few centuries to a couple thousand years. Directions get chaotic in pockets, then the system rebounds to the same polarity. In practice, satellites ride rougher radiation for a few solar cycles. Grids treat storm windows more seriously across a larger footprint. Aviation dose margins tighten on high-latitude routes. Navigation models ship early, then again. Ice cores would later print the story with cosmogenic isotope spikes. The tells tilt toward intensity without global broadening. The eastern SAA minimum deepens fast, while the western lobe drifts, but the belt's width doesn't keep expanding. Assimilation shows reverse flux bridges flare, then recede. The ground residual spikes in amplitude ahead of reshaping, then eases. Secular acceleration bursts clustered in the Atlantic-African sector and sometimes the Western Pacific, followed by partial recovery. The countdown meter jumps, holds a season, then relaxes. Door 3 is stabilization. The choreography gets loud, then lands on its feet. Reverse patches shear, reconnect, and diffuse without knitting the long bridges that undercut the dipole globally. Torsional waves arrive out of phase with the riskiest encounters, damping rather than amplifying shear. The split SAA reshapes, perhaps trades depth between eastern and western minima, but doesn't sprawl. The north magnetic poles sprint kinks as Canadian and Siberian lobes rebalance. Operationally, satellites keep dodging SAA passes. Grids keep storm playbooks sharp. Aviation keeps polar reroutes in the toolkit, but the baseline doesn't trend worse. The tells: assimilation holds reverse flux inside narrower corridors that cycle. Wave phase diagnostics scatter rather than lock. Satellite weak field width stays bounded. The ground network's low-frequency floor thickens briefly, then settles. What turns tells into action are thresholds. Operators don't wait for a label, they watch dials. If the weak field width index rises and stays high, satellites widen avoidance zones and shift high voltage modes months ahead. If torsional wave phase aligns with expected patch encounters across several transits, grid planners schedule storm drills and pre-stage reactive support for the affected longitudes. If a high-latitude stability score slides, navigation agencies push an interim WMM update before error budgets blow up, and drilling firms tighten tolerances where it matters. Misfires are part of a probabilistic world. An amber that fades without a geometry change isn't failure, it's calibration. Publishing residuals, thresholds, and postmortems keeps trust high and improves the next call. Meanwhile, the cost curve favors preparation. Shielding a payload, installing GIC monitors, or moving an upload costs less than replacing a transformer or losing an instrument to an unlucky latch-up. Across all doors, the constant is time. Quantum-anchored networks buy it by holding a stable baseline. Satellites spend it wisely by mapping the shape. Models invest it by turning patterns into short-horizon odds. Whether we're edging into a slow flip, flirting with an excursion, or settling after a wobble, the practical move is the same. Read the dials, move early, and keep the loop tight between sensors, models, and operations.
The meaning. Why quantum physics might predict the flip first. Here's the quiet edge that changes our timeline. Coherence. Atomic magnetometers and NV diamond compasses lock to quantum energy levels that don't drift like coils. Hold that reference steady for weeks, and sub-nanotesla, interannual shifts stop.
Smearing into noise. That stability is why a ground network can stitch nights into seasons and trust the baseline long enough to see the core breathe before satellites publish the headline map. Classical coils sprint, quantum devices marathon. Flux gates and induction coils nail diurnal swings and storm responses, but their calibration and long-term drift make the basement fuzzy. Quantum sensors anchor an absolute scale. Add gradiometry to cancel local clutter, and a deep, slow component emerges. That's where the lead time lives, not in louder signals, but in cleaner persistence that lets tiny accelerations stand out months before geometry changes resolve in global models. Why quantum first, not geology first? Rocks write the after-action report. A lava flow records the field after it cooled. A sediment stack averages centuries. By the time those archives speak, the core's drama is already past. Quantum networks listen in real time. They catch the preamble. Torsional wave trains crossing a corridor. Reverse flux patches edging into alignment. A weak field belt broadening by degrees of longitude. While the system can still wobble, stall, or roll forward. It's not a date. It's a rising probability with room to move. Coherence also shrinks the false alarm tax. With absolute references and synchronized arrays, you can fence the sky hard, model the ionosphere, ring current, and induction, subtract them, and test phase against rotation rather than local time. What survives isn't a rumor, it's a fingerprint that shows up across instruments, software stacks, and latitudes. When that fingerprint thickens over specific longitudes and the assimilation runs forecast a wave hitting a corridor, the odds tilt. You don't need certainty to act. You need credible odds early enough to be useful. This is a culture shift for geomagnetism. For a century, we lived by 5-year models, interim fixes when the pole sprinted, and post-event forensics. Now the loop tightens. Sensors nudge models with live residuals. Models point sensors to the longitudes where the next whisper should rise. Satellites check the shape from above. Operators adjust schedules on the fly. The metronome moves from update every few years to watch the dials this season. There's a practical dividend. A week's warning turns into a safe firmware window. A month's warning turns into a grid exercise and transformer loading plan. A year's warning turns into a refined SAA avoidance strategy and a navigation model shipped before error budgets fracture. Preparation is multiplicative. Small nudges avert expensive nights. That's the core value of hearing the low notes first. Zoom out, and it's the same story across quantum tech. Stable spins and phases turn hidden forces into early signals. Clocks that see gravity's gradient. Magnetometers that hear the ocean's cables. And here, a planet's iron ocean clearing its throat. The field won't flip on our schedule, and we won't stop it. But coherence buys time, and time lets us trade surprise for choice. Coherence turns whispers into warnings. Enough lead time to shift burns, reconfigure substations, and update routes before the squeeze arrives. Want the space weather twist that stacks with these weak field belts? Watch the follow-up next. Subscribe for more evidence-first stories that turn deep physics into decisions you can use.